So this is the topic of exponential function. Exponential function is defined as the inverse of the logarithmic function. So you look at this logarithmic function. So this blue color line is the logarithmic function, which we mentioned this morning. The range and the domains of the logarithmic function has been discussed this morning. The domain of the logarithmic function is from 0 to positive infinity, but 0 is not included. And the range of the logarithmic function is from minus infinity to infinity. So we have the inverse of the logarithmic function, which usually we write it as ln with an subscript of -1 to indicate that this is the inverse of the logarithmic function. And we mentioned earlier on when we study the inverse of a function, the range and domain of the inverse of a function are actually exchanged with the range and domain of the ordinary function. So if the logarithmic function has the domain and range written as from minus infinity to positive infinity, and the domain of this is from 0 to positive infinity, then the domain of the inverse of the logarithmic function is just the range of the logarithmic function, and the range of the inverse of the logarithmic function is just the range, is just the domain of the logarithmic function. So if you understand how the logarithmic function's graph looks like, which is what we discussed this morning, it actually grows increasingly. Ln x is this curve, and the curve of the ln x is an increasing function. But the way how it increases is slowly, it's getting slower. It's increasing, but the rate of its increase is getting smaller and smaller as x growing larger. Whereas the exponential function, which is described as the inverse of the function, which is described as the inverse of the logarithmic function, can be obtained by reflecting the logarithmic function about the y equals x curve. Then this point, which is cutting through the x-axis at 1, 0, would then be projected onto this point, where this point would then be just equals to the point of 0 and 1. And then the function would be like that. So this will be the graph of the inverse of the logarithmic function. And it will cut through this point, which is just the reflection of this point on the logarithmic function. So here you can see that the domain of the logarithmic function is from minus infinity to positive infinity, whereas the range of let me say it again. You can see that the domain of the inverse of the logarithmic function is from minus infinity to positive infinity, whereas the range of the inverse logarithmic function is from 0 to positive infinity, but 0 is not included as part of the range in the inverse of the logarithmic function. And we don't really like to use this symbol to represent the inverse of the logarithmic function. Instead of calling this as the inverse of the logarithmic function, we call this an exponential function. So we have a name for the exponential function, exp with argument of x. This is just to represent the name of the exponential function, which is basically defined as the inverse of the logarithmic function. So in this morning, we first describe and define what is a logarithmic function. Then after we have defined the logarithmic function, we obtain its inverse. The inverse of the logarithmic function, which is the exponential function, exists because the logarithmic function exists. So these pair, the logarithmic function and exponential function, always comes in a pair. Then in this sense, the exponential function is defined based on the logarithmic function. As long as the logarithmic function is defined, then you can reflect the logarithmic function about the y equals to x axis to obtain its inverse, which is the exponential function. And you can see that the exponential function is actually going up exponentially. When its x is increasing, the rate of the exponential function actually goes up very fast. This is in opposite to the logarithmic function. Logarithmic function is increasing, but the rate of its increase is slowing. It's slow down when x get larger, whereas the exponential function, the graph actually explodes exponentially. That means it grows exponentially when x become larger. So this is the general pictures of the exponential function. And at this exponential function, you can see that the point where the e is defined on the logarithmic function, namely when x equals to e, the logarithmic function takes a value of 1. So this is a point where the logarithmic function is equal to 1. Then when you reflect this point about the y-axis, about the y equals to x-axis, then you arrive at this point. So this point, which is 1e, is also sitting on the logarithmic function. So you can see that there should be a point which is equals to here. So here is a value of a number which is e1, and this point, when you reflect onto the y equals to x axis, this point then become 1e. So 1e is the values of, is a point that is sitting on the exponential curve. Okay, so we have to then ask a very simple questions. That is, how do you calculate the values of e raised to the power of r, where e is defined as the Euler's number, which is defined by the logarithmic of e equals to 1. So this is how the Euler number is defined. So we know that the e exists for sure, but e, as I mentioned, is an irrational number. It cannot be expressed as the fractions of two integers. So if you raise the e to the power of r, where r is an rational number, okay, so it is understood that this r is symbolizing an rational number. How are you going to calculate or assign a value to the exponential of, how are you going to assign a value to the natural number e raised to the power of r? Here, sometimes I use natural number e, sometimes I use Euler number. So both of these name, Euler number or the natural number, are all referring to the same number e. So now we ask the questions, how you would assign the value for the natural number e raised to the power of a fractional power r. Now the answer to this is that this number can be equals to just the value of the exponential values of r. So here it looks like it is the same thing. The left is e power r, the right is exponential of r. However, I want to stress that this formula is not really a formula for you to memorize. As I said it again, always in the argument here, we ask what is the values of e raised to the power of r. And the values of e power r is assigned as the values of the exponential of r. Namely, if you have this graph, which is say x and y, and you have the exponential function. The exponential function is given by y equals to exponential of x. So any values of r that you can think of, where r is a rational number that is defined on the x-axis, then the values of ER, that is the E number raised to the power of a rational R, can be just read off from the graph. So the graph of exponent, which is this number, it has an exact number lying on this curve. Okay, so here the number has a value of which is defined as exponents of R. This is to show it is a value that is the values of the exponential curve when x is equals to R. So what we have arrived here at this time is that you define the Euler number raised to the power of the rational R to be the values of the exponential curve where x equals to R. So what happens is that if you are not raising E to an rational number, but instead raise it to an real number instead. You see, the R here is rational number. It is different from a real number. Okay, real number is a number that may or may not be so I think the real number are the set of rational number with the irrational number. So you could divide numbers into rational number and also irrational number. Rational number are numbers that can be expressed as the ratio of two integers, whereas irrational number are numbers that cannot be expressed as the ratio of two integers. So real number comprise of rational and also irrational number. So when we define the e raised to the power of r to be the exponential of r, then we ask this question, can we also define the values of the e number raised to the power of a real number instead of just an rational number? So the answer is yes, because the exponential value or the exponential curve is defined for all values of x. The reason is that the exponential curve is obtained from the logarithmic function. And since logarithmic function is defined for all x, therefore, when you reflect it about the y equals to x curve, the y equals to x line, then every single point on the logarithmic function will be reflected into the exponential curve. In other words, it says the exponential curve is defined for all values of x. So anyway, the argument has to be established rigorously that you can always calculate the values of the exponential. You can always calculate the values of e raised to an real number x, and its value is just can be read off from the curve of the exponential curve. So that is what I want to say for this slide. Now, once we have established that you can always calculate the values of the exponents of e, then the next thing is that the next thing is to look at the exponential function more closely. So from this point onwards, it is understood that all the values of the e raised to the power of x is well defined and is given by this. So now we ask a very simple questions. What is the values of ex when x is taking this number? So if you plot the exponential function as a functions of x, then this is what you get. You get an exponential curve, and you have to know a few properties about this exponential curve. Namely, when x is equals to 0, the exponential values of E0 is just equals to 1. And this is known because the point here is obtained from the reflections of the logarithmic function. See, the logarithmic function is here, ln of x. This is exponential of x. So at the point here, this is 0, 1. So when you make it to the reflections, then this point will be reflected into here. So here is 0, 1, and here, sorry, this point is 0, 1, whereas this point is 1, 0. So here you can see that exp, or e raised to the power of exp of 0, which is the values of e raised to the power of 0, is just equals to 1. And this comes from the fact that it is coming from this point. So after we have roughly studied and mentioned about the properties of the exponential function, then we have to look at a pairs of relationship that relates the logarithmic functions and the exponential function. So this is a very important idea, that functions and its inverse is always behave in such a way that when you slot in a x into the function, and then slot the functions into the inverse of it, this will always give you x. And same thing will happen if you slot in an x into the inverse of the function, and then you slot in the inverse of the function into the function, you should also get back x. So here you can take the f to be a function of log, then the inverse to be the exponential of x. So with this, then you can understand that if you have an x and you take the logarithmic function of it and you take the exponential of it, it's the same as taking the exponential function of x and then slot the exponential function into the log of x. And what you get in both cases, you get both equals to 1. So when you write this in a more explicit form, then this is e raised to the power of ln x, or ln raised to the power of e of x, then both is equals to x. Okay, so this is the explanation for this relationship between the exponential of x and ln x. When I first encountered this relationship in my secondary school, I have to keep remembering I have to keep thinking of how I should remember this formula. However, this formula can be easily understood by referring to what I mentioned here. Okay, the function and the inverse of it, when you operate together, it should give you back the same values of x. Okay, up to this point, is there any questions from the class? Any questions you want to ask me before I proceed on? Okay, so if you have no question, then these are the few examples about the exponential function. So here, the log of e over 2 can be understood to be easily as the, so what is the ln e of 2? So if you refer to this very simple relationship, you can actually answer these questions quite easily. Ln e power of 2. So what is this value? So you can answer these questions by looking at that ln of the, I think we have to refer to this relationship. So you look at this relationship. Ln of the e of x give you back x. So you refer to this relationship. Ln e squared is the same as ln of exponential of 2. Okay, so this is to say you have a 2, you slot into the exponent function, and then you take the log of the exponential function. So this is equals to 2. The reason is because you have a 2, you slot in the 2 into the exponential function, then and you take the log. This is like 2 going to the exponential, and then you take the inverse of the exponential, which is the log, then it will go back to 2. So that is equals to 2. So it is actually easy to write down ln e power 2 is equals to 2, but you have to realize how this formula comes about. So it comes about because of these relationships, okay? So you can also look at this ln e power minus 1, and then you will find that this is just equals to, okay, let me show you how to look at ln e power minus 1. Ln e power minus 1 can be taken as the log of exponents of minus 1. Okay, so this is like you have an x equals to minus 1. You function function of minus 1. Then you take the log of it. Like you take the log of the whole thing. And finally, what you get is that you go back to the same place. So exponential go to here. Log brings you back from exponential back to the original point where you start off with. So it is equals to minus 1. You also have other example like here. An e power of half, square root of half is equals to ln square root of e is ln of e to the power of half, and this is just equals to half. And this is nothing but just sine of x. Now, let me show you how you can see that ln e of sine of x is sine of x. Ln e to any function of x. So here, the u of x is taken to be the sine of x. So here, this is the same as that you start off with an u of x, then you slot it into the exponential function, then you take the log of it. So this is represented by this symbol that you start off with an u, you slot it into the exponential function, then what you get is the exponential function of u. Then the inverse of the exponential function, which is the log, will then bring the exponential of u back to u. So here, finally, what you get is just equals to u, which is just your sine of x. So log of e power sine of x is nothing but just the sine of x. So there are also a few examples that is displayed in the slide here. Then you can try to figure it out yourself. So here, this is just 2. Then I think here is just x squared plus 1. And then this is just equals to 2 power 3, which is equals to 8. Then you figure out this for yourself by using the inverse equations for exponential x and ln x. So let me proceed to the next part. Then this is a very typical questions. You have an exponential function raised to the power of 2k equals to 10, and you are asked to find what is k. Okay, so the way how you do this is to take the log. So you take the log on both sides. Okay, let me write it to form. So this is an equation. So if you take the log of both sides, then this is what you get. So the log of e power 2k is just equals to 2k. So this is just 2k equals to ln 10, and then k is just equals to half. Right, so ln 10 is a log of 10, which you can check it out from the logbook or from the calculator. Then the exponential function also obeys a set of law. That is, if you have e raised to the power of x1 multiply with another exponential function. So the theorem number 1 in the law of exponents for e power x is that if you multiply two exponents together, then the product of two exponential functions is the same as the e raised to the power of x1 plus x2. Then in this case, you can think of the say e power minus x is equals to 1 over exponential of x, then the ratio of two exponential function is just equals to the e raised to the power of x1 minus x2. And the fourth part of the law of exponents says if you have an exponent function e power x, and the whole thing is raised to another power of x2, this is the same as e raised to the power of x2 and raised to the power of x1 again. Okay, so in other words, there's no sort of like sequence in taking the product of x1 and x2. So here you can have e power x1 first, then you take the power to x2. This is to take the e raised to the power x2, then only you take it and raise it to the power x1. So these two, if you write it in this manner, it actually means two different things. It means here you operate the exponential first raised to the power of x1, only then you raise it to another power of x2. In this case, you raise e to the power of x2, only then you raise it to the power of x1. So the sequence is different. Here, you raise it to the power x1 first, and then you raise it to the power x2 later. And this is the opposite in the sequence of how you raise the power of x2. So since there's no difference in the sequence of how you raise the power of x1 and x2, then you write this as x power 1 times x power 2. So it doesn't matter whether it's you raise e to the power x1 first or raise e to the power x2 first, it's the same. It's always given, at the end product is always given as e raised to the power of x1 and x2. And this theorem 3, you have to know it by heart because you need this a lot when you are dealing with exponential function. So this is a proof to the law of number 1, namely how do you know that the product of the two exponential function is equals to e raised to the power x1 plus x2. So this is not simply assume, right? You don't simply assume that these two must be equals to this one. You have to prove it. So this is how you prove it. First of all, you label e power x1 by y1, then y2 equals to e power of x2. Then what you do is from here, you take the inverse of the function. That is, you take the log of y1 and you take the log of y2. When you take the log of these two equations, then e power x1 become x1. When you take the log of e power x2, then you get x2. So you add the x1 and x2 together, then you end up with the summations of log of y1 and y2. And earlier in this morning, we mentioned that if you have the sum of two logarithmic terms, is the same as the product of the term a and b in the logarithmic function. Therefore, from here to here, you are applying the properties of the summations of two logarithmic functions. Now, once you have arrived at this, then you have x1 plus x2 equals to the log of y1, y2. So then what you do is that you take the exponents on both sides. So when you take the exponents on both sides, this will give you the exponential of x1 plus x2. And what is the other side? This one, when you take the exponential function of the log of y1, y2, what you get is just y1, y2. Okay, so can you see that you have originally y1 and y2, you slot it into the logarithmic function, then you take the exponents of it. So taking the exponents is like taking the inverse of the log. Therefore, you start out with y1, y2, go into a log, then go to exponential, then you end up the same locations of y1 and y2. So this is y1, y2, and when you write it down, y1 is just this one, y2 is just this one. Therefore, you prove that e raised to the power of x1 plus x2, which is the exponents of x1 plus x2, is just simply equals to the product of e power x1 and e power of x2. Okay, so that's how you prove the law of the first the law of exponents in the theorem number 1. Then let us try to see how to simplify this. So how do you simplify this? To simplify the first part, you use this law that if you have an A plus a B, then this is equals to e power A times e power B, right? So this is the applications of the law that we just study. So you have e of sum of two terms is the same as the product of these two. So here this is true. So here the x is my A, ln2 is my B. So this is the same as e. So let me write it down here. E power of ln2 is the same as e power x times e power ln2. Then you can simplify this further. E power ln2 is just equals to 2. Then this is just the exponential of ex. So this will give you 2 times exponents of x. Likewise here, exponents, the e raised to the power of minus ln x can be expressed as e power ln of x raised to the power of minus 1. Okay, so this is the law that we have to just learn. And this is a law that says minus ln x is the same as ln x raised to the power of minus 1. So this is the law that we learned this morning, that if you have x raised to the power of r, you take the log of it. This is equal to r ln x. So this is the law that we learned for the logarithmic function this morning. So when you set r equals to minus 1, then you get this one. Okay. So I have then expressed minus ln x as ln of x raised to the power of minus 1. And then this is nothing but just equals to x power minus 1. And this one is e power 2x divided by p power 1. So here we can write this as e power of 2x minus 1. So that is the solution based on the law. I think specifically based on this law. Okay, e power x1 over e power x2 is just e power of the difference in e x1 and x2. So here we have done the part C of the questions. Then part D is to say e power 3 raised to the power of x is the same of e raised to the power of 3x. This is to make use of the fourth law of the exponents. Therefore, here we have just demonstrated to you the applications of the power law for the exponential function. So these are all simple algebra. I believe that most of you have actually seen this before in your secondary school before you enter USM. So the next bit we want to talk about is about the derivative of the exponential function. So here we have a very interesting thing to talk about. That is, what is the derivative of the exponential function? So here we define the exponential function to be e power x, or sometimes you just write as e power x. So my question is that what is dy dx? So how do you calculate that? How do you explain dy dx is equals to, so for those who have experience with this, the derivative of the exponential function is just the exponential function itself. But can you explain how this comes about? Okay, so let's see how you explain that. In order to obtain the derivative of the function dy dx for y equals to the exponential function of x, what you have to do is to resort to the theorem, to one of the topic that we have learned earlier on in topic 7.1. Namely, if you have a function and you know its derivative, then the derivative of the inverse of the function, okay, this is the derivative of the inverse of the function, can be expressed as in the form of the derivative of the function, where the derivative of the function is evaluated at a point where x is equals to the inverse of x. Okay, so this is the relationship that we have discussed a few times already. Therefore, if you look at the logarithmic function, and you know the logarithmic function has a derivative. The logarithmic function's derivative is 1 over x. Therefore, by knowing the derivative of the logarithmic function, you can then calculate the derivative of the exponential function in terms of the derivative of the logarithmic function. Okay, so you can always use these relationships to calculate the derivative of the inverse of a function if you know the derivative of the original function. But the trick here is that you have to evaluate the x in the derivative of the function at the inverse of the function. Okay, so if you were to proceed, then let us see how you do that. I hope that I'm doing it correct because I have to record this from my memory. So according to the formula I just mentioned, this is the same as the dx of the logarithmic function evaluated at x equals to the inverse of the logarithmic function, which is x as e. Okay, so this statement is the statement that x is to be evaluated at the inverse of the logarithmic function, which is the exponential function. So let us see if I can derive the formula for the function correctly by using this method. So here is 1 over the derivative of the logarithmic function. So the derivative of the logarithmic function is 1 over x. Okay, and it's to be defined at x evaluated at the exponential of x. So here this is just equals to the x, where I'm going to replace x as the exponential of x, which is just the exponential of x. Okay, so when I see at x, I replace x by the exponential. So I arrive at the very simple result that the derivative of an exponential function is the exponential function itself. Right, so this is to be weird because if you compare with the other function, for example, x power 3, then after you have taken the derivative of the power function, the order of the power is always reduced. Yeah, I think it will always be reduced to 2. And if you take a derivative of a higher order n, you always reduce the power by 1 order, like this. Okay, so that explains the meme that I put up. I think this meme is quite interesting. So imagine you have original functions, then you take the first derivative, you take the second derivative, then the function becomes slimmer and slimmer. However, if you take the derivative again and again and again, the function doesn't change at all. It remains the same guy, the same fatty guy. This guy is the exponential function because whenever you take the derivative for n times, you always end up with e of x. So that is a very important result for the exponential function. Namely, the derivative of a function is equals to the exponential function itself. So here is a very simple questions. That is, you write the function u to represent e power x. Then you would want to calculate the dx of u by using the chain rule. So using a chain rule, you have this is a chain rule, right? I'm not saying this is chain rule, du dx, as maybe this is not really a chain rule, so I don't need to use a chain rule. So what I need to do is that d dx is just equals to d dx of 5ex is just d dx of e power x, and this is just equal to 5 e power x. So this is an extremely simple example of differentiating a exponential function. Then the next thing we want to do is to generalize the result of the differentiation of the exponential function. Now, up to this point, the e is to be raised to n power of a single variable x. And if you differentiate it with respect to x, you get ex itself. So when I say I generalize this, what I mean is that I promote x to become a function of x instead of just an x itself. So in that case, I ask the question, what is the d dx of e raised to the power of any generic function? Okay, so this is a generalization of this term where instead of e power x, I'm asking e power of n function of x. In the special case where the function of u is just equals to x, then we would have this relationship instead. So this is a general situation for e raised to the power of u. Then you can actually answer these questions by using the chain rule. So if you use a chain rule, then this is equals to e power u du, and then you have du dx. So this right hand side is just the applications of the chain rule, and du of e power u is just eu itself. Then here we have du dx. Then this is just the general results. When you are differentiating e power u, that is what you will get. Okay, so let us look at an example that is specified in this case here. I think it doesn't give you a good example. Let's see if I have an example. Not quite though. We have only integrations, but not the differentiation. But anyway, I have just shown you can prove these results of e raised to the power of EU. Now, why we need this result? The reasons we need this result because we want to know what is the indefinite integrations of e power u. So let me proceed and tell you how I lead to the next step. So up to this point, I have shown you that you can obtain the derivative of the exponential function where e is raised to the power of u as du dx times e power u. So I'm going to integrate the relationship on both sides. So what I do is that I put both into an indefinite integral operations. So this is a symbol of an indefinite integral. So I'm going to slot this into the indefinite integral. This is d dx of eu. And then here is eu, e power u, du dx. Okay, so what I'm doing here is that I'm taking the antiderivative of both sides of the function. I'm taking the antiderivative on both sides of the equation. So this is the antiderivative of the left term, and this is the antiderivative of the right term. Remember what I mentioned? If you are looking at this indefinite integral, what this represents is the collections of all the antiderivative to the function of fx. So here, capital function f represents the antiderivative of small function fx. So this whole thing represents an antiderivative. So I'm seeking the antiderivative of these equations on both sides. Then I'll look at this function a little bit more carefully. So let me see what I would get from here. So here on the left hand side, what I would get is that I have d of eu, and then I have dx. So let me see how I proceed from here. So finally, what I want to do is that I want to show you that from this very simple differential rule, then you would finally lead to the fact that e raised to the power of u. When you integrate with respect to u, you get e power u plus c. I think that is what I want to show you. This can be easily deduced from this relationship. It is easily deduced from relationship. So I try to do it, but probably I better not do it here. I better refer to the lecture notes, because the lecture notes show you all the details of the steps, how this formula arrived at. So you can show this relationship by looking at this differential equation. Okay, so this differential equation says the derivative of e power u is e power u du dx. So you use the relationship between an antiderivative and the integrating function, then you'll be able to show that this is the case. So let me see how I would look at this more carefully. Let me see. Okay, so here is what I was looking at just now when I write it on my whiteboard. So this is a relationship that I have written. If you look at this more carefully, finally you will show that this is just equals to e power u plus c. Now, I was thinking to explain this in more detail, but then I changed my mind. I think I'll let you to try to figure it out for yourself. So anyway, you can also try to understand how this formula comes about by referring to this slide. So at the end of the story, what I want to tell you is that if you have e raised to the power of u, where u is any function of x, then the indefinite integrations of e raised to the power of u is just e power of u plus c. Okay, so that is the result that we are going to make use of in the next example. So say what is e power of 3x dx integrated from 0 to ln2. So let us try to write these equations in the in my whiteboard. So how to calculate the e power of 3x. Let me check again. I keep on forgetting my slide. E power of 3x. Okay. The x, and you integrate this from 0 to ln2. So you can perform this very simple integration by substitutions. That is, you let u to represent the general functions of 3x. Then you would convert the integrations from integration with respect to x into the integration with respect to u. So you write down du as equals to 3 dx. Then the integration can then be easily converted into e power u. And this 3x is just du over 3. And then here is x equals to 0. Here is x equals to 2. Therefore, since u is equals to 3x, when 3x is equals to ln2, then u of ln2 is just simply equals to 3 of ln2. Okay, so u is 3 times x. When x is equals to ln2, then you just replace x by ln2. Then when x is equals to 0, u at x equals to 0 is just equals to 0, because u and 3 are related. Therefore, the integration with respect to x, when you change it into the integration with respect to u, then you're integrating it from u at x0 to u at x equals to ln2. So this is the same as the integrations. This is the same as the 1/3 multiplied with the product of u at ln2 and u at 0, which is 0. U at ln2 is just equals to this number, 3 of ln2. And what is this? This is the result of the integrations of e power u, which is just e power u. Therefore, you end up to be just 1/3 e power of u, where u is 3 ln 2, minus e power of u at 0, which is just 0. So here you have 1/3, and then you have e power ln 2 raised to 3 minus 1. Now e power 0 is 1. I mentioned that earlier on. That is 1/3. Then you have here 2 to the power 3, because you have exponential raised to the power ln, and then this would be just your function minus 1. So it will be 1/3 8 minus 1, which is just then 7/3. So according to my calculations, this will be just equals to this number 7/3. Now I might be wrong, but you can always check this yourself using mathematical or using rule from alpha or using whatever method you can think of. So that is the example of A, 7A. Then we can try to do example 7B. Okay, so example 7B. Example 7B is the integrations of e power of sine x and then cos x dx, and integrate it from x from 0 to pi over 2. So this integration can be easily calculated by using some simple substitution. But still, you have to understand that you have to make use of the result. E power u du is equals to e power u plus n constant. So here you have to make some simple substitution. Here, obviously, the substitution is to make u to represent sine x. When you make these representations or this substitution, then e power sine will become e power u. Okay, so then this integration would then just become e power u. Okay, so what is the cos x dx? Once you have defined u to be your sine x, then it is quite straightforward that du is equals to cos of x times dx. So this is the differential of u, and the right hand side is obtained from the differential of sine x. Therefore, cos x sine x is nothing but just your du. Then you have to make some substitution. That is, when x is equal to 0, u is just sine of 0, which is just 0. And then u at pi of half is then equal to sine of pi of half, and this is equals to 1. Therefore, here you have u equals to 0. Here you have u equals to 1. Then finally, you end up with the e power u evaluated between 1 and 0, then you have e power 1 minus e power 0 is just equals to e. Okay, e minus 1, because e power 0 is 1. So that is the answer to the example 7b. So here is the very simple calculations that tells you what is the exact values of e. That is, if you take if you take, for example, the logarithmic function of y to be fy, then you take the first derivative of the function and you write the derivative of the function in its definition form. Then you make some simple steps and just follow through these steps. Then finally, you show that the values of the e number, the natural number or the Euler's number, is just equals to the limit of this very complicated function, 1 plus x raised to a power of 1 over x, and let x to goes to 0. So that could be easily done in a computer. If you sit in the computer class, you can actually write a simple code to evaluate the number e using this very simple approach. So usually the natural numbers such as e and pi, and what else? There are also other fractional numbers such as square root of 2 can always be practically calculated using programming method. So this is just the values of E. It can be easily derived by following this slide, which I'm not going to go into detail. Okay, so up to this point, I hope that you can still hold on and can stand another half an hour of lecture. Can you? Okay, so I think it's 9 o'clock, 9:30. The next few slides would be slightly more heavy. The next few slides is about applying the exponential function and generalize it to the exponential function of the form a power x. And then probably we will not going to continue with this lecture tonight because it's already late, but I'm going to record another half an hour of lecture to explain slide number 27 up to the last slide on this topic of exponential function. Hey, so it has been a very hectic lecture. I have to go very fast because we have not enough time to finish covering the syllabus. So it's already 9:31. I thank you for attending my lecture. I'll see you again tomorrow morning. It will be an tutorial session. Okay, so I'll see you tomorrow morning. That's all. Any other questions? You can stay back to ask me.